The distribution of many different quantitative variables fits the shape of what is called the normal distribution. Examples of normally distributed variables include blood pressure and even major league batting averages. In this chapter, for variables that are normally distributed, we will find a very handy way of interpreting the standard deviation. So let's begin and explore an interesting interpretation of the standard deviation, one that allows us to make comparisons. Suppose I took two exams, a history exam and a statistics exam. I received the same score on both exams, namely a 93, which is better than the class average in both cases. The class average on the history exam was 88, and on the statistics exam it was 85. But there was a lot more variability in grades on the statistics exam because the standard deviation was 15, whereas on the history exam the standard deviation was only 5. Now the question is, on which exam did I score better compared to the rest of the class? If we compare my score, which is 93, to the class mean, it seems that I did relatively higher on the statistics exam, because on the statistics exam I did 8 points higher than average, whereas on the history exam I only scored 5 points higher than average. This analysis, however, does not take into account the variability in the exam scores. Remember, there was a lot more variability in the statistics exam scores. So in each case, we will take this deviation from the mean and we will divide by the standard deviation. The 8 points higher than average is divided by the standard deviation of 15, resulting in a 0.53, which says that on the statistics exam, I did about half a standard deviation above the mean. If we divide the deviation of 5 by the standard deviation of 5, this turns out to be 1. So I scored 1 whole standard deviation above the mean on the history exam. So since I scored a higher number of standard deviations on the history exam, we will decide that relatively speaking I did better on the history exam. Now the computation we just did turns out to be very important. We calculated what is called a z-score. We took whatever score we received on the exam, compared it to the class mean, and divided by the standard deviation. This gives us a number called a z-score. Z-scores do not have any units. This is because the units in the numerator are the same as the units in the denominator, and since the units are the same, they cancel. What a z-score tells us is how many standard deviations above or below the mean we are. A z-score of 1.5 tells us we are 1.5 standard deviations above the mean, whereas the z-score of -1 tells us that we are 1 standard deviation below the mean. Later in this chapter, we will return to z-scores and further explore how they can provide important information about our studied variable when our variable is normally distributed. But first we must officially define what it means for a variable to be normally distributed. Many quantitative variables have what is called a normal distribution. Some familiar examples are height, weight, blood pressure, SAT scores, sleep times, and many others. Normal variables follow what is known as the empirical rule. So here is what has to be the case for a quantitative variable to follow the empirical rule. First, it has to have a nice symmetrical bell shape. Skew distributions do not follow the empirical rule. There are also 3 percentage requirements. Not all symmetrical distributions are normal. It must be the case that 68% of the observations fall within 1 standard deviation of the mean. Additionally, 95% of the observations must fall within 2 standard deviations of the mean. And finally, almost all, or 99.7% of the observations, must land within 3 standard deviations of the mean. The definition of what it means to follow the empirical rule is so important that I'm going to ask you to memorize it. Many texts refer to it as the 68%, 95%, 99.7% rule. Perhaps thinking of it in this way might help you remember these important percentages. At this point, we will look at a few examples that will illustrate how to use the empirical rule to answer certain questions about normally distributed variables. So, for our first example, imagine that it takes us, on average, 20 minutes to commute to campus every day with a standard deviation of 2 minutes. Suppose also that your commuting time is normally distributed. That is, it has a nice symmetrical shape and follows the empirical rule. How can we use this information to answer 2 very specific questions? First, how often or what percent of the time will you arrive on campus in less than 22 minutes? And secondly, what percentage of the time will it take you more than 24 minutes? Now, the secret to answering questions similar to this is to take the time to examine closely what the empirical rule says in this problem situation. First, recall that the mean was 20 minutes and that the standard deviation was 2 minutes. Then decide what happens 68, 95, and 99.7% of the time. The most effective way to understand how to apply the empirical rule is to draw graphs to represent each of the 3% mentioned in the empirical rule. We start by drawing nice bell-shaped curves. Since the mean commuting time is 20 minutes, we put 20 at the center of the curve. Now, since the standard deviation is 2 minutes, on either side of 20, we're going to go up and then down in increments of 2. So we start at 20, go up to 22, 24, 26, and 28. Start at 20, go down to 18, 16, 14, and 12. Now, the reason I stopped at 12 and 28 is because then we would be 4 standard deviations away from the mean. And the empirical rule tells us that hardly any observations are more than 4 standard deviations from the mean. In fact, 99.7% are within 3 standard deviations. So we can see that it would be very unusual for me to take longer than 28 or less than 12 minutes to commute to campus. Now we apply the empirical rule, and we see that if we go 1 standard deviation on either side of the mean, which means commuting time between 18 and 22 minutes, we will capture 68% of the cases. So that 68% of the time, it'll take me between 18 and 22 minutes to arrive on campus. Similarly, if we go 2 standard deviations above and 2 standard deviations below the mean, we will have captured 95% of the cases, and we realize that 95% of the time I will arrive on campus between 16 and 24 minutes. Finally, if we go an interval of 3 standard deviations above and 3 standard deviations below, we capture almost all, or 99.7% of the cases. So 99.7% of the time, you will make it to campus in between 14 and 26 minutes. Now we have to use the 3 graphs to answer the original questions. One question is, what percent of the time will it take you less than 22 minutes to get to campus? The key is to recognize that 22 minutes is exactly 1 standard deviation from the mean, so we will use the first graph. We know that 68% of the time we arrive on campus between 18 and 22 minutes, but that is not the question that was asked. Thinking a little more and using the fact that the graph is symmetrical, we realize that if 68% is in the middle, that leaves 32% for the 2 tails. And since it's symmetrical, that 32% will be split evenly between the upper tail and the lower tail. So 16% of the time it will take us more than 22 minutes, and 16% of the time it will take us less than 18 minutes. In the bottom graph, I have shaded precisely what the question asked, 22 minutes or less. There are 2 ways of thinking of this. You can think of this shaded area as consisting of the 68% that is in the middle, plus the 16% that's in the lower tail, and add 68 and 16 to get 84%. Or you might think of the entire shaded area as representing 100%, subtract the 16% in the upper tail, leaving you 84% in the lower tail. Either way you think of it, 84% of the time you will arrive on campus in 22 minutes or less. The other question we were asked is, what percent of the time will it take you more than 24 minutes? First, you must ask yourself, how far away from the mean is 24 minutes? And we recognize that 24 minutes is exactly 2 standard deviations away from the mean. So we'll use our 2 standard deviation graph to help us. Once again, between 16 minutes and 24 minutes accounts for 95% of the time. If there's 95% of the time between 16 minutes and 24 minutes, the rest, namely 5%, is equally split between the upper and lower tails. 2.5% of the time it will take you more than 24 minutes, and 2.5% of the time it will take you less than 16 minutes. So we have the answer to our question. The question asked, what percent of the time will it take you more than 24 minutes? And the answer to that is 2.5% of the time it'll take you more than 24 minutes to arrive on campus.